Hey everyone, welcome to a new week here. Very special week. If you haven't already seen, please look on the Google Classroom there in the COVID or the COVID-19 section where there is a sign-up sheet if you wish to come in this week for extra support. I do want to stress that I'm not teaching anything new if you come into extra support. It's just purely to give you a hand if you do need one-on-one instruction or one-on-one help, right? Only a maximum of 6 people can come in the room at a time. The whole thing is written in the post there, and I'm going to post there should be some extra notes on the safety guidelines there that you all need to be aware of. But that's it. So hopefully I get to see some of your faces next week. If not, we're going to continue on with the remote learning that we're doing right now, and we're jumping into the part 2 of 2 of our points and lines here. So we're aiming to, in this note, to look at how we can determine the system solution by graphing it, and then how we can determine the number of solutions that two linear equations might share. You might be wondering, well, how can there be more than one? And we'll talk about that towards the end of this note. So hopefully this will be under 20 minutes. Well, let's dive right on in here. So normally, over the past bit, you folks have essentially just been given a point or a few points, and you've been asked to figure out whether that point satisfies the system of linear equations. And you plug it into both equations, and out pops a point. So what we're going to learn today is kind of a more exact method that gives us exactly what the solution to a system of equations will be. If we're not given a point that we're just going to test, this one will always pop out a solution if there is a solution. So essentially graphing gives us a more exact way to determine the solution. And I'm going to put S in brackets here because it could be more than one solutions for a linear system, right? For a linear system. So let's look at an example of this. And we're told in example 1 here, determine the solution of the following linear system. And we're going to be doing this. Normally I would put actually determine the solution by graphing. I didn't put that in there. That was my bad there. But what we're going to do, we're going to bring in a sticky of our grid. We'll go black. We'll make it the finest grid that we can. And we need to recall that the solution occurs at the point of intersection, right? Because if we're drawing 2 linear equations, 2 linear lines, the only solution that they're going to have, if they have one solution, it's going to be the point at which they share that same x and y coordinates. So that's the point of intersection that we can think about here. So we need to determine how we can actually go about finding that. So I'm just going to move my graph over here for now. And we have 2 equations here. I'm going to give them a label just so that we can kind of keep things straight here. Let's call this equation 1. And let's call this one over here, let's call this one equation 2. And we know how to graph these, right? These aren't in our normal slope-intercept form, but we can make them in slope-intercept form, and then we can go about graphing them. So let's do that. Let's start by figuring out slope-intercept form for number 1. 1 is slope-intercept, okay? And if you don't know how to do this, I highly advise that you go back and check on how to convert to slope-intercept form from the first part of this. Or actually, it might have been even it was in the linear functions unit. So go refer to that if you don't know, if you're not confident with doing this, because it's going to be used quite a lot. And you can see how these skills build on one another. So slope-intercept. So we need this in y equals mx plus b form. So what's the easiest thing to move right now? Well, I'm going to move that negative 3x to the other side. So we get positive 3x minus 20. And then we want y in its own. So I'm just going to divide by 2 on everything. So we get y equals 3 over 2x minus 10. So there's our first one here. In slope-intercept, this is equation 1. Okay, what about equation 2? Let's do equation 2. And again, I'm not going to teach how to do this in this note because you should be doing the work yourself to give yourself enough practice to be able to do these. So I'm not going to go step by step as I go put these in slope-intercept. So we got 2 slope-intercept. And what do we got here? We got 2x plus 3y equals 9. All right, so I'm going to move that 2x to the other side by subtracting it. And I'm going to divide everything by 3. So get y equals negative 2 over 3x plus 3. And here is number 2 in slope-intercept form, right? And we know how to graph these. So let's start with number 1. And let's draw our grid first. Let's draw our grid first. So we have our y-axis, we have our x-axis, y, x, okay? And so let's start with our y-intercept. We know our y-intercept in this case is -10. I don't think I have 10 points on this line, so I'm going to count by 2's. So in this case, we're going to have 2, 4, -2, -4, -6, -8, -10. Again, this is 2, 4, 6, 8, just to make that explicit. And on that -10 point, I am going to draw a point, just like that, okay? So I have -10, and now we need to figure out the second point. We can use our slope. We can use our slope and that -10 point, and the slope is telling us that we need to rise 3 units, and we need to go over to the right 2 units, rise over run, right? And it's a positive slope, so we should be rising up and going to the right in the positive x direction. So we got 3 over 2, right? Yeah, so we'll go up 3. So we got to be careful when we're counting this because I did go by 2's. So up 3 would actually be 1, 2, 3 right here. And then over 2 units would be 1, 2. Could do that again. 1, 2, 3, and then over 2, 1, 2. Just so that we get 2 exact points here. So beautiful. Let's draw that. Oh my gosh. That one should be better. Not quite. 1, 2, 3, 2. There we go. Let's try something like that. So there's our first line. And let's try our second one now. So our second one, what was our y-intercept? It was +3. It's +3. So we're going to go up 1, 2. Here's +3. And where is our, so we're going, we can either go down 2 units or we can go to the left 2 units. We just had to put that negative onto one of these numbers here. I'm just going to put it onto the -2. So we'll go down 2 units, so 1, 2, and we'll go to the right 3 units. 1, 2, 3, right here. So here's our first point over here. Forgot to label that. Here's our second point. I'll go down 2. Right, 1, 2, and I'll go over right 1, 2, 3. And actually, what we're going to have to do is you see that this line, this pink line is actually, we can extend it a bit more. And you might be able to see where this line's actually going to go, right? So there's that. Let's just extend that. And let's draw our red line here. And forgive me, this might be absolutely horrendous, but let's see if we can get this in one go. Not quite. Not quite. Oh, that's feeling good. That's pretty good. That'll do for now. Okay. This would be a lot easier if I had a ruler, but alas, I do not. Okay, let's label these lines just so that we're not getting too confused. So what did we say this pink one was? Well, this was our y equals 3 over 2 x minus 10. And what do we say that our, what did we say? Sorry, what did we say that our 3 was? Or number 2? Number 2 was y equals -2 over 3x plus 3. Okay. Beautiful, beautiful, beautiful. And we can see the point where they intersect here, right? They intersect right at this point right here. And what point was that? Well, we said that this was, we can just measure this on the line. So this is our solution to the system. And which point is this? Well, this is point. Remember, we're counting ones on our y-axis, so we got negative, or sorry, let's do our x first. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. We have 0.6, and then -1. And that's it. So what we can say is, therefore, what was our original question? The solution to the system is 6, -1, right? And that's all you need to write. And you're off to the races. So you're looking for the point at which 2 lines intersect. And if you're finding that they're not intersecting, sometimes what you will have to do is just extend a line, right? I had to do that here because I didn't draw my pink line long enough. But if you extend it even more, then you'll see that there is a nice point where they do intersect. So there is that. That is the general basis on how you're going to solve anything like this, where it's asking you to determine the solution of the following linear system by graphing. You got to convert to slope-intercept. You have to convert to slope-intercept. Graph both equations. And then finally, determine point of intersection. point of, I'm going to just call it POI, point of intersection, okay? Oops, should be an E. And so that's it for that one. So what about when we're looking at the number of solutions? And you might be wondering how there can be more than one solution for a line. And you don't know this yet, but you do have an intuition as to how we can actually have more than one solution. So what I'm going to do, I'm going to bring in just a few stickies here. I'm going to bring in a few stickies. And let's change it up so that we have, let's make them kind of tiny. So we're going to have 3 different scenarios here. And 3, right? 1, 2, 3, beautiful. And we were talking about this more in the linear functions unit when we were talking about perpendicular and parallel slopes, right? So when we were talking about, I'm just going to draw some grids on all these guys. When we were talking about perpendicular and parallel slopes, we were comparing slopes and we were asking ourselves whether or not 2 lines are perpendicular to one another or whether 2 lines are parallel to one another. And when we're looking at more than one equation with respect to this, or more than one linear line or equation, that has a big thing, that has a lot to say about how many solutions something has. Because let's consider the first scenario where we have 2 parallel lines. And remember, 2 parallel lines, we said that they're parallel if they share the same, they're parallel if they share the same slope, right? So we have 2 parallel lines here. I'm just going to change the color of this guy just to match, just to show them 2 different here. So here we have parallel lines. And let's say that I told you to graph those 2 lines. Let's say that before we even drew them, I gave you 2 equations and told you to figure out how many solutions this system would have. And you found out that they're both parallel. Well, how many solutions does this have? How many solutions does this have? You have a general intuition about this. Parallel lines, what's special about them? Well, they're never going to cross, right? They're never ever going to touch. They're growing at the exact same rate. They're going in the exact same direction. They're never, ever, ever going to touch. And so what we can say about a parallel line is, well, if they're never going to touch, we have never touch. They're going to have 0 solutions. I mean, you can continue all of them on to positive infinity and negative infinity and go as far as you want to the x-axis. You're never going to get a point at which those 2 lines touch. Never, ever, ever going to get a point in which 2 lines touch. And so just remember that they have the same slope. So what about a different one? Let's consider perpendicular lines. Let's draw a line here, and let's say that's our perpendicular. That's one of our equations, and we'll draw another one which is coming at it just like this. Okay. And we said the perpendicular lines is just, we take the equation of one linear equation, and we're taking the slope and we're flipping it and then making it negative. And what you'll notice is, well, how many solutions would a perpendicular line have? How many solutions would a perpendicular line have? Well, it has only one solution here, right? One solution, because the lines are crossing exactly at one point. So they will touch. So touch at one point, which means that they're going to have one solution. And let's give an example actually for both of these. So let's just make up an example. So let's say that one of those lines was y equals 2x plus 3, and one was y equals 2x plus 1, right? These are both going to have no solutions, right? Because they have the same slope. Well, what about perpendicular? Well, same kind of idea, right? We're just going to have, instead of having a same slope, 1 over 2x plus 4, y equals negative 2x minus 7. They just have different slopes, and they don't have to have that flipped fraction and then flipping the sign. But perpendiculars are just a nice way to kind of talk about this. As long as the slopes are different, here, they're going to have one solution. So as long as slopes are different, they're going to have one solution. As long as slopes are different, okay? So they don't have to be exactly perpendicular slopes. And then we're going to have one more here. And we haven't really talked about this, but let's consider something like this. So what if we had a line? And then what if we had another line that went right on top of it. So basically the exact same line. How many solutions is that going to have? And what we call these lines is typically coincidental lines. Coincidental. And these ones have, I mean, if you can think about it, they have an infinite amount of solutions, right? Because they're always crossing each other at every single point along the X and Y axis. Along the, So what we have is they're touching all the time. What we could say is then they have an infinite solutions. There is no end. Infinite solutions. And this only occurs when slope and y-intercept are the same. And we're going to look at an actual example of this. I'm going to talk you through it and we'll figure out, hey, what's going on here. So let's look at this one. Let's look at the example 3 here. And we need to determine the number of solutions for the following linear system. We have two equations here. We have 4x minus 6y equals negative 18 and 2x minus 3y equals 6. What's nice about these is we don't have to graph them. We just need to put them in slope-intercept form and compare the slopes and the y-intercepts. So put in slope-intercept form. Oh my gosh, I'm at the school and the lights keep turning off. I'm in the dark. Forgive me, folks. Here we go. Okay, I'm back on my computer. So let's label these again. What color system did I use before? I used pink and red. Yeah. Let's do pink. Let's call this one equation 1. Let's call this one equation 2. And let's put 1 in slope-intercept form. Slope-intercept. Okay. So we have 4x minus 6y equals negative 18. So I'm going to get that 4x to the other side. So we have negative 6y equals negative 4x minus 18. Now we need to get rid of that negative 6. So I'm going to divide everything by negative 6. And what do we get? Well, we got y equals negative 4 divided by negative 6. We can reduce that, right? We can make that positive 2 over 3 if we divide both of those by 2. 2 over 3x. And then negative 18 divided by negative 6. Well, that's just 6, 12, 18, positive 3. So here's equation 1. And let's do number 2 here. So we'll split this up and we will do, what did I do it in again? Red. 2, slope, intercept. What do we get? 2x minus 3y equals 6. Let's get that 2x to the other side. So we're going to subtract it. Okay. And we'll divide by negative 3. And we get y equals 2 over 3x minus 2. Beautiful. So we have both equations here. We don't need to bother graphing because we're just being asked to figure out how many solutions it's going to have just at all. And so what do these two share in common? What does 1 and 2 share in common? Well, they share the same slope, right? But they have different y-intercepts. So they're not going to, even though they share the same slope, they can't be coincidental because they don't have the same y-intercepts, but they are parallel, right? Because they have the same slopes. So what we could say is, well, this one, we could say, therefore, since 1 and 2 share the same slope, but have different y-intercepts, there is no solution to the system. And this is always for this unit, this is something major that I always want you to do is to communicate what your answer means. So again, since they have the same slope but different y-intercepts, they're parallel and they're not going to have any solution. So only 2 more examples here. Let's look at this one. So determine the number of solutions. So let's look at this one. So again, we're going to take this and we're going to call this equation 1. Go my red, we'll call this equation 2. Okay. And let's solve 1. So 1. Here we go. We got 5x minus 3y equals 6. Okay. I'm going to move that 5x to the other side. So we get negative 5x plus 6. I'm going to divide by negative 3. And we get y equals positive 5 over 3x, right? Because that negative and negative is going to make it a positive, minus 2. And here's equation 1. Beautiful. Okay, let's do equation 2. We have 20x minus 12y equals 24. And what do we got with this one? Well, let's move that 20 to the other side. So negative 12y equals negative 20. X plus 24 Let's divide by negative 12. And what do we get? Well, we get y equals 20 divided by 12. You can divide by 4 on each of those. So that was going to give us 5 over 3x, positive 5 over 3 because there's 2 negatives there. And then 24 divided by negative 12, that's minus 2. So how many solutions is this one going to have? Let's compare the equations. We have y equals 5 over 3x minus 2 and y equals 5 over 3x minus 2. They're the exact same equation. So therefore, they're coincidental, right? They're coincidental based on the fact that they have the same slope, and they have the same y-intercept, the same slope, 5 over 3, and the same y-intercept, negative 2. So therefore, since 1 and 2 share the exact same slope and y-intercept, since they share the exact same slope and y-intercept, they are coincidental and have infinite amount of solutions. I just use the infinite sign there, just a bit more shorthand, right? That's all we need to put. And we got one more here, and I'm sure you can guess what this one's going to be. But anyways, let's just power on, right? Okay. So we have equation 1. We have equation 2. Let's do 1. We have x plus 3y equals negative 6. Let's move that x to the other side. So we get negative x minus 6. Let's divide by 3. We get y equals negative 1 over 3 times x minus 2. So here's equation, this is equation 1. And let's do equation 2. Negative 4x plus 3y equals 9. What do we get with this one? Well, let's move that negative 4x to the other side. So we get positive 4x plus 9 divided by 3 all the way through. We get y equals 4 over 3 x plus 3. Equation 2. Okay. So 1 and 2, let's compare them. Do they share the same slope? No. Do they share the same y-intercept? No. So they share nothing in common. So that means that they're going to intersect at least one point, right? Because they're not parallel. They're not coincidental. They don't sit on top of one another. So they're angled slightly differently because they have different slopes. They're going to cross at some point. We just don't know where, but we don't really care for a question like this. So what we can say is, therefore, since neither equation shares the same slope and y-intercept, the system will have one solution. So this ended up being a little bit longer than I anticipated. What are we at right now? Let's see. Yeah, 28. Sorry, folks. Anyways, that is the gist of what's going to go on this week. I think I am going to shorten my output for the next little bit, just to 2 videos a week, which we won't be able to get through everything. Like, we're not going to be able to get through the finance unit, and we might be lucky if we get to trig. So we'll see what happens. But that is it, folks. So please, if you want to come in anytime this week, make sure that you sign up on the Google Doc there. And I hope to see some of your faces soon. All right. Take care, everyone. Please refer to the homework. I'll post the solutions the day after. Awesome. Have a wonderful, wonderful week. Take care. Bye.